Hello, welcome. So this is our first of some of the extra bonus lectures not actually included in the 192 course this semester, but things that I think are really cool nonetheless, and really kind of highlight how the universe is a lot more weird than we might expect it to be. So, these next four lectures are all actually going to be about relativity. So relativity initially came out from, as we have seen before, Maxwell's equations. Maxwell defined that electromagnetic waves propagate at a certain constant speed c, right? 1 over square root of the permittivity constant times the permeability constant, which is E naught times mu naught. Square root of that under 1 gives us 3 times 10 to the 8th meters per second, which we know now as the speed of light. One of the big controversies at the time when he came up with something like that is that a lot of people assumed, okay, well, that's in the rest frame, which is essentially if you're standing still and I shoot a laser pointer, that's how fast the light travels. But if I run alongside of it, then of course it should travel a little bit slower. And that actually wasn't the case. Einstein was one of the first ones to illustrate that, hey, maybe this is not just true in the rest frame, maybe this is true in all frames. And these frames that I keep talking about, we haven't really discussed in depth that much so far. So that's a lot of what today's about, to really highlight that. And I'll get back to that point in just a little bit. But before too much longer, we might ask, why would we even study relativity? This is on kind of the outskirts of physics as we might discuss it. Relativity is realistically not useful for a lot of people. It might be useful, or might be very useful for some people in particular. A friend of mine actually works on these GPS satellites where relativity does become a real factor. And she certainly didn't expect to need relativity in her career, but that's just kind of where she ended up. So I'm not assuming that that's going to happen for many people. I'm assuming that most of you will not have to worry about relativistic effects because, for the most part, they're very, very tiny for most of our day-to-day lives. We'll find essentially where the limit is. But it is still very cool. Miami is a liberal arts college, which means the liberal education is essentially you're not just studying your one single focus. You are focusing on this thing, but you have a broad perspective. You have to take multiple classes in things outside of your particular career so that you've kind of got a broad perspective on your field, other fields, things like that, right? So it's a lot of fun to look at. It's really cool to look at. We're not going to dive super deep in any particular detail, but I think it's a fun thing and worthwhile to talk about regardless. So, you might ask the question, who's the most famous physicist ever? And I imagine that a lot of you would immediately point towards Albert Einstein because it's Einstein. But there are actually a lot of people, so this is not just one particular time period, but this is probably, mostly the 20th century is where a lot of these people became very, very important. But these are all huge names, right? Every single one of these people has made massive contributions to the field of not only physics, but all sorts of different things. They don't have to be limited to one particular field to make their contributions, but they are all making very, very, very significant impact. We had kind of like a renaissance of physics at the beginning of the 20th century, and these people were all big parts of that. But you can imagine here that the most famous equation of physics, the one that every single person always touts out, the constant if somebody gets hit by the smart beam or whatever sci-fi nonsense, they always start to spout out Einstein's energy relativity equation, right? E is equal to mc squared. It shows up everywhere. I've got it on mugs of mine. You can see Dr. Alexander posing with the giant statue of Einstein with E is equal to mc squared written on it. It shows up everywhere, right? It's kind of like a pop culture icon almost, but maybe a little bit more nerdy than that. But what we're actually going to find, not today, but very soon here, is that it's actually in this form not completely correct. This always gets under my skin just a little bit, that this version of the equation is actually incomplete. It's only for a special case that E is equal to mc squared. But by the end of our stuff with chapter 36 here, we're actually going to go through and derive this equation for ourselves. So there's a little bit of satisfaction, kind of our goalpost at the end is to derive the most famous equation in physics. But a lot of what we're talking about here is what I'm going to call special relativity. Right? Special relativity and general relativity are two slightly different things, and general relativity is, well, as you probably know by now, the things that are more general are generally more difficult, is what they mean with that. It hits a broad number of cases. That's where you talk about stuff like the curvature of space-time and things like that. That's a little bit out of our wheelhouse for this go around. But focusing on special relativity, we can still talk about a lot of the really cool effects that come from relativity, things like time dilation and length contraction and things like that, the stuff that gets really weird and funky. But first, before we get into that, we need to talk about how we viewed reference frames for a very, 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 very long time. And those reference frames are part of what we call Galilean relativity. So this is kind of intuitive, right? If you're driving on the highway and there's a car that pulls up right beside you, your velocity relative to that car that's beside you is 0. You see them as stationary. They see you as stationary. If somebody goes a little bit faster, say you're going 60 and they're going 70, then you see them moving relative to you 10 miles per hour. It's the difference between those two, right? It's what you view them as, not the objective somebody standing outside watching you go by on the highway, not the copper holding out the radar gun to try and catch you speeding, right? They would see a little bit of a different scenario, but from your perspective, sitting inside the car, that car that's speeding by you right now is going 10 miles per hour relative to you. Now, if they're going the opposite direction, if you're in the truck in this case, so if I'm looking at this picture, if you're in the truck going 60 miles per hour and the car is coming at you at 70 miles per hour, you see them traveling towards you at a speed of 130 miles per hour, 70 plus 60, right? That's their relative velocity to you, because from your perspective, you're sitting right there. You're not moving, but they are moving at 130 miles per hour towards you, and the road is moving at 60 miles per hour towards you. So it's all about from the perspective that you're in at this moment in time. That's really the tricky part, and it's a little bit difficult to hold on to. But we've got a few other things here that it's going to hopefully help us describe this a little bit better. So when we're talking about things like space-time and things happening and everything else, we're going to define any sort of thing that we're interested in as an event. So maybe a star explodes in space. That's an event. That happens at some place in space, XYZ, at some moment in time, T. Right? So we could draw this out somewhat like this graph right here, right? This event, maybe the sun is exploding or something like that, right? That happens at a certain location at a certain time. And those 4 variables describe that event. Now, all of that is taking place, these axes that we have, we call that an inertial reference frame. And an inertial reference frame is a scenario where the reference frame is at some constant velocity, which is very important, right? Because we can have multiple reference frames. Like what we've got down here in this picture, what we're really seeing here is I've got one reference frame in black and one reference frame in blue that's moving. So let's go back to this picture. For example here, again, let's imagine that we've got the cop sitting there watching for people that are speeding. That cop is in an inertial reference frame where the velocity is 0. The truck is in another inertial reference frame. From the truck's perspective, you're not moving, but the cop is. From the cop's perspective, they're not moving, but you are. And that's how we can have these moving reference frames. That's the scenario that we've got. Now, if you start accelerating, everything falls apart. We don't want to talk about acceleration yet. We want to just assume that we're dealing with constant velocity scenarios. But cars moving at a constant speed or standing still or something like that, all of those are valid inertial reference frames. And for every single one of those, they might see events happening at their own specific places, right? If S prime has moved some distance away and it sees the same star explode, they might see that happen at a different point in space relative to them, right? If I'm sitting right here and I'm 1 meter away from my camera, but my hand is right here and it's only 0.5 meters away from the camera, we see things happening on the camera. If a bug flies onto the lens of the camera, we would see that happening at a different point in space relative to us. My hand sees it as 0.5 away, I see it as 1 away, things like that. So, a concept check here, and I'll let you look at this for a second. Which of the following scenarios are good inertial reference frames? And let's assume for a minute that the Earth is stationary in the universe, not spinning, not hurtling through the universe, through the Milky Way, none of that stuff. Just think about your daily life kind of here. We don't really feel the effect of the Earth spinning around or anything like that. So let's take that as kind of like our ground, our basis. But piece by piece, what I can imagine here is that our house, I'm sitting in a house right now, I don't think it's moving. That's a good inertial reference frame. That works. A car rolling down a steep hill. We can imagine that the car is going to start accelerating, right? There is going to be a little bit of friction, but I imagine it's going to be speeding up as it goes down that hill. Not a good reference frame. Let's go ahead and draw these things out, actually, while we're talking about them. So this one, check. X. A train coasting on a level track. So this one's kind of a maybe, because I imagine that the friction does play an important part here, but if we don't look for too long, we can imagine. So let's do like a squiggly here. It's kind of like a maybe, right? Maybe if the friction isn't too great, it works out pretty well, right? If you've ever seen a train about to get stuck on the tracks or something like that, it seems like they never slow down. They just keep rolling by at the exact same speed. And that's because they've got so much mass to them. That friction is really not a huge deal. So I'll put that as a maybe. Like kind of yes, but maybe there's a little bit of acceleration. It depends on how much we can ignore friction. A rocket being launched? Certainly not. That's got a constant acceleration to it. Finally, a skydiver falling at a terminal speed. That actually does work, because terminal speed means that we don't have any acceleration, so we are moving at a constant velocity. So that's kind of what we're expecting. C could go either way, right? I wouldn't be upset as long as you've got some sort of good reasoning for what you're talking about in C. I would be fine with, say, calling that one either way. So, when we're talking about these different reference frames, we need some way to make sure that everybody can agree on what's going on. So I'm actually going to go into a slideshow for this one because I've got, I want to write this one down. So our Galilean transformations are really telling us, okay, well, let's go back to our speeding car example. The car sees one thing, the cop sees something else. How do they agree? They agree through a Galilean transformation. So if these are all Galilean reference frames, then Galilean transformations are how you talk about what happens between two reference frames. So let's imagine that we've got two inertial reference frames, S and S prime, and at t is equal to 0, they're overlapping, right? So they're essentially, all of the axes are lining up at t is equal to 0. S prime is moving though. S is not. So S prime has been moving along, and at some time after 0, something happens. An event happens. Now, because of all of this stuff, and I realize I'm kind of blocking some of the screen in the corner, but I'll talk through all these details. In S, that happens at X, Y, Z, and T. In S prime, that happens in X prime, Y prime, Z prime, and T prime. Now, for Galilean transformations, we can relate a few different things here. So we can agree kind of right off the bat, the y-axis and the z-axis is not changing, right? Just because it's moved over, it doesn't mean like how high up it's moved hasn't changed. How far over it is hasn't changed. But how far forward we are, that x-axis, that has changed. But I think we can all agree that if I have a stopwatch and you have a stopwatch and you run 10 meters away from me and we both click our stopwatch at the exact same time, it would read the same time, right? So t is equal to t prime, but x is equal to x prime plus however far s prime has moved since we started recording. Now, if we were to have some sort of rocket, so it's not an event, but something else happening, some other object that has its own velocity, right? Like a rocket ship has a velocity u. If I was to try and describe what happens there, my transformations will look kind of similar. I would have a similar position argument, But if I want to take the derivative of that to think about how is that position changing, what I would end up finding is that the velocity of the object in S is equal to the velocity of the object in S prime plus however fast S prime is moving. And I know that's really wordy, and I know that's got some complicated things, but go back to this picture. Right? Think about the reference frame of the cop, the truck, and the car. The cop sees the blue car in this bottom picture right here, moving at, and let's put it right here. So here's our, we'll call this one S, we'll call this one S prime. In a case like this, S sees the blue car moving at 70 miles per hour to the left. S prime sees the blue car moving at 130 miles per hour to the left, right? So it's adding those two together to get the velocity of our object. So, and it's all about perspectives, right? Imagine yourself in the scenario. Don't try to take an outside perspective here. The outside perspective is different from the perspective of somebody in the seat of one of these vehicles or something like that. So let's imagine a baseball pitcher can throw a ball with a speed of 40 meters per second. He's in the back of a pickup truck that is driving away from you. So you're standing there, he's standing in the bed of a pickup truck, and he throws the ball at you. But it only moves towards you at 10 meters per second. You catch it, and you're kind of like it almost falls out of the glove, right? It really doesn't sink into the glove or anything else like that. It's a pretty slow 10 meters per second. What is the truck's speed? This is easiest if we draw a picture. So what I'm going to do, I'm just going to draw it on this slide too. So let's imagine that we have, I don't know, what does Cybertruck look like? I'm trying to remember. Something like this, right? And then like the bed of the car is in there, some stupid thing like this. I don't know. The thing looks ridiculous. Let's go ahead and imagine our picture standing right here. So this is our moving frame. This frame is moving like this. It's got a certain velocity to it. And this is the velocity of the truck that we're after. But since this is our moving frame, I'm going to call this one S prime. Now, from S prime, the pitcher throws the ball, and the ball speeds out. And I'm going to call this one U. So my V's got like the little tail. U looks kind of like this. I'm going to call this one U prime, comes out at 40 meters per second going to the right. From the perspective of S, which is not moving, you're standing right here, and you see the ball approach you at 10 meters per second, which we'll just call U. What is the truck speed? And I think you can kind of look at this and have an idea of what the number is, but I wanted to go through all these steps anyways and think about this equation right here to really define what's going on. Right, we're going to take this bottom equation that I've got highlighted here, and I'm going to say, okay, well, U is equal to U prime plus the velocity of the frame as it's moving, which is the velocity of the truck. Right, so we can see here that the velocity of the truck should be something like 30 meters per second going to the left. So it should be a negative 30 meters per second going to the left. And that's what we've got, right? From the perspective of different people, things will change slightly. So, let's look at another one. Let's imagine a newspaper delivery boy is riding his bicycle down the street at 5 meters per second. Can throw a paper at a speed of 8 meters per second. What is the paper's speed relative to the ground if he throws the paper forward, backward, or out to the side? So this is going to be another one. Drawing pictures is the most helpful thing you can do. So we have to imagine that we are standing from the side, right? We are somebody watching him. We're standing on the sidewalk, watching him go down, throw these papers in different directions, right? Maybe he doesn't care about his employment and he's just throwing these things any which way he wants. Or maybe we've put him up to it for some sort of science experiment. I don't know. In any case, we have to imagine this thing. Let's take a top-down view. From our top-down view, Here is the bicycle moving at a constant 5 meters per second. Reference frame S prime, because this is the moving reference frame. So if this is the moving reference frame, or let me draw this like this. Let me do this in a slightly different way, actually. The more I'm thinking about this, the more it might be a little bit better if we try something else here. Let me not take a top-down view. Let me take a side profile, and let's look at A and B first. And then we'll kind of use that argument to come up with what should be going on with C. So I'm going to draw out my S prime, and we say S prime moving with the bicycle. The reference frame of the bicycle is moving this way at a rate of 5 meters per second. And here's, I don't know how to draw a bicycle. Something like this. Right? This is what bicycles look like. I don't know. I haven't been outside in so long. So here's the reference frame of the bicycle moving to the right at 5 meters per second. And then we say, okay, well now from the perspective of the bicycle, from the perspective of the boy on the bicycle, he throws it forward at 8 meters per second. So here is our something like that. That's what a paper looks like, I think. Moving this way at 8 meters per second from the reference frame of the bicycle. So this is U prime. Read from the S prime perspective, it gets U prime. From somebody else's perspective, from our reference frame S, now if we're just standing still watching this, we saw this thing moving at 5 meters per second, and then he throws something that was already moving at 5 meters per second. He adds another 8 to it. So what we would see, the paper in our perspective is going to be moving forward at 13 meters per second. And again, I'm going to use this equation. U is equal to U prime plus V. That's what gives me my 13 meters per second. So we can imagine, hey, let's take the exact same argument. Let me take this thing and let's no longer turn it this way. Let's say, hey, I want to turn it around the other way. So I don't know which direction this thing's going now, but if I look at this thing and I say, hey, now it's going this way instead. Now U prime, if I think about it as a vector, is going in the negative direction. So negative 8 meters per second relative to the bicycle, right? He turns around and throws it that way. So now what we would see is actually it would turn around from our perspective, right? It's now going that way. Our U value is going to be negative 3 meters per second. We see the paper traveling to the left, but it falls a lot slower than it would if he had thrown it directly at us. So negative 3 meters per second backwards. So now, this to the side kind of scenario, you might already have an idea of what this is going to look like in your head. Now I'll take this top-down perspective. Now it's a little bit more useful. Now we can imagine that the bicycle itself is already moving at 5 meters per second. But the paper gets thrown out at 8 meters per second. So this equation that we had just looked at doesn't quite work anymore in the same way, right? Because that equation worked really, really well when we're talking about movement along the same axis, right? Notice that the velocity as we're talking about this thing, we're looking at the x components because S prime is moving in the x direction. So in a case like this, that transformation doesn't quite work anymore, but you can imagine that even if the reference frame is moving, well, that just means that that velocity hasn't changed. Right? If I'm thinking about the x component as I would have seen it, so here is my x direction, and let's call this direction z. So we can imagine that if we're looking at these two axes, then what we've really got here is that our x velocity hasn't changed. U of x is still 5 meters per second. But now U of z is 8 meters per second. So our total velocity at the very end of the day, we just have to essentially combine these components together, right? I'm going to take 5 squared plus 8 squared, take the square root of that. So that's 25 plus 64. I'm going to pull up my calculator before I get something wrong on this one. But if we take the square root of that, we should find a final speed of something like 9.43 meters per second. And that's what we've got. Now again, in all three of these reference frames, from the perspective of the boy on the bicycle, the newspaper is always moving at 8 meters per second. He's got a very consistent arm, right? He always throws it at exactly 8 meters per second. But from our perspective, because he's throwing it in different directions each time, the speed changes each time. So, we've got a few of these different things. And this is one of the ones that we'll talk about only a little bit. Acceleration gets really, really messy really, really fast. But if we have some other external object accelerating, so for example, this delivery boy was going down a hill, accelerating, then, well, that's not a good perspective. That's not a good, let me wipe that one back a little bit. Let's not take that because that's an accelerating reference frame, right? That makes a bad inertial reference frame. We have to imagine if we have somebody that is traveling by car and somebody sitting down and they're watching a rocket launch through the air, right? That rocket's accelerating the entire time as it goes up into the air. We would both see the rocket with the same acceleration, even if our perspective of its position was different. That's what we're getting from this. Acceleration is the same in all reference frames according to Galilean relativity. So, this is a fantastic picture to draw out. It's very, very helpful to have. But anyways, so let's imagine at t is equal to 1 second, a firecracker explodes 10 meters away from the origin in the reference frame S. 4 seconds later, so this is t is equal to 5 seconds, a second firecracker explodes at now 20 meters away from the origin. Reference frame S prime is moving in the x direction at a speed of 5 meters per second. Assuming that both of these frames lined up at t is equal to 0, what are the x coordinates and the time coordinates for these two events happening in S prime? So, pictures are going to be eternally useful here. So I'm going to actually draw this one out, though. We need plenty of space to actually work with this one. So the first thing that I want to do is I want to draw out what S looks like. So we've got something like this. We call this S. We call this X. And we say from the perspective of S, something happens at X is equal to 10. And something happens at X is equal to 20. So we have our first explosion. That looks like an explosion, right? This happens at t is equal to 1. Then we have a second explosion. We have to imagine maybe there's some different colored fireworks or something like that. This blue explosion happens at t is equal to 5 seconds. Now, I think this is easiest to imagine. Picture you're walking towards this. Somebody's sitting down. Somebody has just lit 2 firecrackers. And you, pyromaniac that you are, start walking towards those firecrackers. Where do those things happen now relative to you? So if I have S prime, maybe not, let's not draw it right there. Let's draw this thing. So I'm going to draw this in, I'll do it in like this. No, I'll do purple. I like purple. So let's draw this kind of like this. So we have to imagine that at t is equal to 0, these two things lined up exactly. But S prime is moving forward at a speed of, I've already forgotten, 5 meters per second. So if you're walking towards the firecrackers and you move 5 meters per second, in the first second, when that firecracker explodes, you have moved from 0 to 5. You're at 5, the firecracker, from the S perspective, is at 10, so you see that as being 5 meters away. Hopefully that all makes sense right now. Right? But I really encourage you, if this is a little bit strange to look at and strange to imagine, and I know I'm slightly in the way on this thing again. So I've got, let me move myself down here. Let's do that. That's a little bit easier to see. Now I've got S and S prime moving to 5 meters per second. I really do encourage you to imagine yourself standing still and then walking. And those are the two reference frames. The walking is S prime. The standing still is S. Now look at things happening as you go back and forth between those two reference frames. You see the exact same things happening, and from Galileo, we see them happening at the exact same time, right? We might remember that transformation that we said the time part is actually the easiest part here, because in the Galilean transformations, t is equal to t prime always. The stopwatches the two people have always read the same value. So we can start that right off the bat, right? We could really say right here that this is also equal to t prime. Blue t is also equal to t prime. Right? It's the same in both perspectives. But the position has changed. And so what we're going to need to do for that, we're going to need to take that transformation. The x, where something happens, is equal to where it happens in the prime frame plus v times t, right? Just what we saw in our Galilean transformations. Now we're going to rearrange this a little bit. We're going to say, okay, well, I don't care what's happening. I know where the things happen in x. I want to know where they happen in x prime. So let's take the red firecracker then. So we say in the red perspective, we had, I find myself a little bit of space here. X is equal to 10. T is equal to 1. V is equal to 5. I should probably write some units on these things. So with those three details in mind, then I can say, okay, well, let me rearrange this thing. Let me solve this out for x prime. X prime is equal to x minus vt. That is to say, 10 meters minus 5 times 1 is equal to 5 meters, which is exactly what we talked about when we first approached this particular problem. Right? In 1 second, you have stepped forward by 5 meters. You see the firecracker 5 meters away from yourself. And that's exactly what we get. So now let's do this from the perspective of the blue firecracker. Now this is kind of 5 seconds in. This is a little bit more confusing to see. But again, in the exact same scenario, the event happens at 20 meters from S's perspective, from the seated audience. From the person walking, this happens at 5 seconds in from the time we started walking, and we've been walking at the same pace the entire time. So now what's happened, we rearrange this again. We say x prime is equal to x minus vt. So I have 20 minus 5 times 5. This is negative 5 is where this happens. So we have walked past the blue firecracker before it exploded. Now it's happening behind us, right? Don't look at the explosion. You're cooler that way. But these are two answers. Go ahead and highlight that in red instead. Let's keep that color coding going. So again, it takes a lot of visualization to really get your head around this sometimes. And I know that is oftentimes the most difficult part of dealing with a lot of these problems. So draw out plenty of pictures, really imagine yourself, go back and forth, physically move. That really does help you understand what S prime looks like. Okay, so let's go back though. Now, there's a little bit of an issue. When I talked about the Galilean transformations, so they're called Galilean transformations because Galileo Galilei came up with them, right? Like, they are old at this point, and they were useful for a very, very, very long time, right? They still are not useless because for the most part, this all works out very well. Cars, newspapers, baseballs, a lot of these things make a lot of sense under the Galilean transformations, and that's why reality has essentially agreed with these equations. Or they has almost agreed. There are only very, very slight circumstances where we run into just a little bit of an issue. And that was really kind of illustrated when we talked about what happens with light. Here's the problem with light. It doesn't care about what reference frame you're in. It moves at c. So if we were to take this picture that we've got right here, and we were to say, okay, well, S prime maybe sees it as c, but then S would see it as c plus v. But that doesn't quite work. And this was the big part, this was the big sticking point why a lot of people disagreed with Maxwell's equation at first, or they didn't even disagree, they just misunderstood it, right? They thought that the speed of light was in reference to the reference frame, to the stationary reference frame. You're holding the flashlight, so you see it as c, and everybody else sees it as something different. Galileo is saved. But that's not the case. Special relativity has two big things. The laws of physics don't change depending on what reference frame you're in. Right? That's a really big sticking point. All of our things, and this is what we expect, right? Newton's laws do not change just because you're moving. Stuff like that. All of our equations still work even if we are moving at some constant velocity. It doesn't require us to be stationary. The second one, and the one that we really haven't talked about to this point, is that the speed of light is constant in all reference frames. And this actually makes a really interesting point, and when I get to the chapter 31 lectures, I'll talk about this a little bit more. But things like the electric and the magnetic fields, you might remember that the magnetic field needs a moving charge, but from different reference frames, from the charge's reference frame, it's not moving. From our reference frame watching the charge, it is moving. So when I say that the electric and the magnetic fields are really the same force, it's because the magnitude of the field, of which field you have, differs based on your reference frame. Which is a really strange thing to wrap your head around, but it's a really cool kind of deal, and all four of Maxwell's equations are necessary to get all reference frames included, and not just our outside perspective reference frame. But I'll talk about that in a little bit more detail in chapter 31. So, a couple of questions here. A starship blasts past Earth at 2 × 10⁸ meters per second, 2/3 the speed of light. It fires a laser at the back of the starship. What is the speed of the light as it approaches Earth? The answer is the speed of light, 3 × 10⁸ meters per second. An out-of-control alien spacecraft is diving into a star at a speed of 1/3 of the speed of light. At what speed relative to the spacecraft is the starlight approaching? Again, 3 × 10⁸ meters per second, the speed of light. A positron moving in the positive x direction at 2/3 the speed of light collides with an electron, the speed of light. From all perspectives, the speed of light is a constant value. And that's our timekeeper. It tells us how time moves. Time can't move faster than light allows it to. So this is where our Galilean relativity starts to break down. What we really run into is that in Galileo's relativity, it always assumed that we could take these linear transformations and that the time could be agreed upon regardless of reference frames. But then, we've got a way to describe these. The Lorentz transformations does not make that assumption. It holds c to be the time limit of the universe, or the speed limit of the universe, and it says, hey, what if the time doesn't have to be an agreeable value? What do these transformations look like now? And these are what are known as the Lorentz transformations. Let me go through very fast. Let me pull myself up here, and let's go ahead and look at this thing from the current slide. I got a couple animations on this one as well. This says, consider 2 inertial reference frames that overlap at t is equal to t prime is equal to 0. So right when we start the stopwatch, we overlap. Then we have s and s prime overlapping each other. After some time, an event occurs, just like we saw with Galileo. But now, with our handy-dandy speed limit of the universe, we still have our events happening, x, y, z, and t, x prime, y prime, z prime, and t prime. But now, t and t prime are not necessarily the same. And the Lorentz transformation tells us that now we have this wacky-looking thing. That x is equal to gamma times x prime plus v t prime. And t is equal to gamma times t prime plus vx prime over c squared, c being the speed of light. What is gamma, you might ask? Well, it is this Lorentz constant that comes up depending on the speed of the reference frame. So at the very minimum that it could ever be, it's 1. But any other time than that, it's going to be greater than 1. And we kind of look at this and we say, hey, when does this factor actually come into effect? Right? This equation that I have right here, let me back out of this for a second. This equation that I have right here, that looks, well, pretty similar to what we just saw with the Galilean transformations, right? It's still x prime plus v times t. If t and t prime are not that different, when can we assume the Galileo works? And look at this. This is v squared over c squared. In all of our approximations and neglecting the very, very, very tiny terms, we can imagine that 10 meters per second compared to 3 times 10 to the 8th, and then square that, that's a negligible speed. That's why most of the time we don't notice any of these effects. It's not until you're moving at very, very, very fast speeds that this ever starts to become a real factor, right? Or you're trying to be very, very, very precise about some of those numbers you're going for. So that's why this doesn't show up all the time, but this is the more accurate, albeit more complicated, picture of the universe. So, with all of these things in mind, let's try this. Let's say that a rocket travels in the x direction at a speed 0.6 c with respect to Earth. And I'm going to recommend don't try to multiply 0.6 times 3 times 10 to the 8th. Just leave it as 0.6 c and plug it into our gamma. That helps a lot. An experimenter on the rocket observes a collision between 2 comets and determines that the space-time coordinates of the collision are x prime, t prime is equal to 3 times 10 to the 10th and 200 seconds. So that's our x prime and our t prime. Remembering here that if we're moving in x, then y and z don't change. What are the space-time coordinates of the collision in Earth's reference frame? So, let's assume here that, again, they're overlapping to t is equal to 0, right? So they pass Earth right at t is equal to 0. Calculate the answer using Galilean coordinate transformations first. And then calculate using Lorentz transformations, because what we're really trying to do here is prove that the Galilean doesn't get us close anymore. The Lorentz is the correct one. But, show why Galilean transformations just don't work at relativistic speeds. So, we really, really, really need to draw a picture for this one. It's just super helpful. So what I'm going to draw here is we have Earth. And Earth is in a reference frame, S. Our stationary frame. The rocket ship, and we'll draw this one in red again, in S prime, is moving this way at a speed of 0.6 times the speed of light, right? So not a slow speed by any means. And let's draw out a really bad rocket real fast. So we've got something like this, rocket things, right? And a little peephole so that we can actually see these comets explode. So we said from S prime's perspective, we saw this explosion occur, and this explosion occurred at x prime is equal to 3 times 10 to the 10th meters, t prime being 200 seconds. And I want to make sure that I got those numbers correct. 3 times 10 to the 10th and 200 seconds. Yes. Excellent. So now let's start with our Galilean transformations to try and figure out what this would be. And our Galilean transformations did I spell that right? These are the questions that we want answered. Galilean, that looks correct. In our Galilean transformation, we would just say, hey, t would also be equal to 200 seconds. We can all agree on that, right? X is equal to x prime plus v times t. x prime, 3 times 10 to the 10th, v times t. Now we do actually have to plug this in. So that is 0.6. Let me go ahead and write that thing out real quick. So we would say the velocity is 0.6 times 1.8 times 10 to the 8th meters per second. 1.8 times 10 to the 8th meters per second. Multiply that by 200. 360 times 10 to the 8th, or 3.6 times 10 to the 10th. We would end up x is equal to 6.6 times 10 to the 10th meters. That's what we would see from Earth's perspective, according to Galileo. Now, the much cooler transformation, the Lorentz transformation, says, no, that doesn't work. We need a few other things. We need first our gamma value. So gamma is equal to the square root 1 minus, not plus, v squared over c squared, all under 1. So this is where I'm going to plug in my 0.6 c squared over c squared. The c squareds cancel. And I've got 1 minus 0.6 squared. That makes that whole thing a lot easier to deal with. So 0.6 squared would give us something like 0.36. 1 minus that value, take the square root of that thing. And we should end up with this is 1 over 0.8, or 1.25. That is our Lorentz factor for this particular problem. So now we need to go back to those Lorentz equations. We need to say, okay, now as we're trying to calculate these things, let me start with x. X is equal to gamma times x prime plus v times t prime. Gamma times x prime plus v times t prime. We plug in all of these numbers together, and what we end up finding at the end of the day is that x now should be 8.25 times 10 to the 10th. Oh, my drop pad stopped working on me. And this is a strange ordeal. This is farther away than what we expected to find. And the Lorentz transformations have a lot of weird effects like that, because the photons are always moving at the same speed relative to every single person, and that means time is slowing down if you're moving faster. So you saw this thing happen in a certain place from the perspective of the rocket ship, but because since you're speeding up, time is moving slower for you, it's going to take a longer time for that to get to Earth. It's going to be a farther distance away. This really is where stuff starts to get a little bit messy and strange. So now we need to do the exact same thing for t, actually, though. So we look at our equation for t, and this is the more complicated one because it's got this mess in it. But let's go ahead and write this out. We just follow this equation on this one. And we say, okay, well, this is gamma times t prime plus v x prime over c squared. And I check my units for this, and I say meters per second times meters over meters per second squared. We are left with seconds at the end of the day, right? So our units do match up for this fraction here. But we plug all of those numbers in, and what we end up with is 325 seconds. So not only do the people on Earth see this at a distance farther away, they see it even later than we do in the spaceship. And I know this is a lot to wrap your head around, and the Lorentz transformations are very, very, very strange. There's a lot of fantastic demonstrations and a lot of different videos that I'll have that will hopefully illustrate this a little bit more to help you with your visualization of this. But from an insider perspective here, visualizing special relativity is incredibly difficult. Don't worry if it's very complicated, if it's very confusing. It is very confusing. It's very strange, and this is one of the weird ways that we have tried to unravel the universe and found what's inside. But anyways, that's going to close it out for 36-1. Next time we'll be back with even more on our Lorentz transformations.